Welcome back, everyone. Sorry I have not been able to make a quantum mechanics video for a little while. I've been real busy with work and travel, and it's just been chaos with how life has been. That being said, I'm real happy with how the article reviews came about because they were very interactive, and it sets a great tone for what we're going to probably have to do in this chapter, dealing with some of the articles that come about when dealing with identical particles, in particular bosons and fermions. And we'll see how they create ramifications in the later theories, especially if you want to be in particle physics, QFT, anything like that, they will always be there. That being said, this particular question is asking us about if psi A and psi B are orthogonal and both are normalized, what is the constant A in equation 5.17? And this is equation 5.17 where we see we have a psi plus or minus with two locations now, so two radial components, and radial is not necessarily the accurate word, but the position vectors themselves. And we see that we have state A at position A, state B at position 2, B at 1, A at 2, things like that. Now these upper signs, lower signs, they do represent something with the type of particles we have. And when we're dealing in two particle systems, we mainly branch into bosons and fermions. And this is what we call the symmetrization condition or symmetrization axiom. Very important, and it has a lot to do with this later, and we'll deal with that in due time. But with this construction leads us to part B. If psi A equals psi B and assume normalized, what is A then? This, of course, occurs only for bosons. And the reason why is because we know, thanks to the Pauli exclusion principle, that fermions cannot occupy the same state. Now, how to read this equation, we see that fermions are the lower sign and bosons are the upper sign. And what this tells us is that this plus sign and the plus sign here represent the same state for bosons. What this tells us is that bosons can occupy the same thing, no problem. Fermions, however, are anti-symmetric under interchange. So if we assume that they were able to be in the same state, you will just get a wave function at 0. So it's not going to work, and that's exactly what the Pauli exclusion principle highlights to us. So this problem is not too bad, does highlight a lot of stuff, and it'll be pretty quick. We just have to be careful with the bookkeeping. So with that, let's dive in. Stop number 1 then on this journey is let's revisit what it means to be normalized and the normalization condition, which means that the magnitude of the wave function squared under all the directions, things of that nature, equals 1. Now, this is a little different, and the notation gets dense and messy, and that's why it's just better to break this up by parts. Here, the D through R1 just tells you that this is the position vector for location 1. So if this is at x1, y1, z1, this might be at x2, y2, z2, and this accompanies the 3 integral here, the 3 integral there, things of that nature. This is just a much more compact notation. This author likes it, and several others like it too. But other books will simply go to the bracket notation just because this is not that nice to actually work through, I don't believe. But nonetheless, understand that this is a 3-dimensional volume integral, volume as well. Just you're trying to get all the spatial coordinates covered. That's what they're trying to highlight. They just condense it to a position vector 1 and a position vector 2. It's a little bit neater for what we're dealing with. Then moving on, we see that we need to take the magnitude of the wave function squared. Of course, we know that this is just the complex conjugate times the thing itself. No big deal. We just have to be careful because we have 1, 2, multiplied in another 2 terms, so it's just the same thing as any other binomial expansion. Just have to be careful not to mix up the R1, R2 with states A and state B. So be very careful, but other than that, I think we can get through this pretty fast. Wonderful, wonderful. So with this, after we see the distribution, which if you want a little more slow segue approach, again, the PDF is in the description like all the other videos for these later chapters. Go ahead, check that out. But what we see here is that the first terms, we just get the magnitude of state A at R1, magnitude of state B at R2, easy enough. Then we have plus or minus for a couple of these cross term, so to speak. Yeah. So here we see all our 1's together, all our 2's together. Then we have the opposite side where we have B and A switched. Complex conjugates kind of stay the same, but again, plus or minus with those cross terms. And then finally, we have a singular plus sign here with state B at R1 and state A at R2. Now again, whenever we multiply these, we multiply the signs across accordingly. So this would be a plus to a plus and a minus to a minus. Two minuses make a plus, so that's why we end up with a singular plus there. So if you're algebra or you're just copying and pasting in your notebook, be aware that that goes to a singular plus sign, and not to be alarmed when you see it not pop up or when you're just writing plus or minus. This is supposed to be there. Alright, that being said, if this is the magnitude squared, let's plug it into the integral, and we could see that we can now go, once we plug this in, to the orthogonal condition and cancel out some stuff. So you see we have the first term, the second term, and let's get on to the third and fourth. Alright, so yeah, so now we have the third term and the fourth term here. Wonderful, wonderful, wonderful. Let's kick all the constants out front, make the cleanup a little easier. Now, remember real quick that they stated that these things were indeed orthogonal. So since we have A and B, that goes to 0. Since we have B and A, that goes to 0. B and A, that goes to 0. And we see, lastly, that we have A and B goes to 0. Notice that the color coordinates, the color scheme here is that everything in green is at position 1, everything in blue is at position 2. That kind of helps you separate how messy these things can be in actuality. Finally, what we see after that is that we have the plus sign on the last term in that expansion, and we just kind of clean it up there. Again, now that we see that we have orthogonality, taking out those, we see that the normalization conditions can get these down to, let me change colors, these down to 1 and 1 across all the magnitude squareds. So we should be pretty good to go in the cleanup step on the next slide. Let's check it out. All right, so as we suspected, the cross terms here went to 0, 0, 0, 0. Thank you, orthogonality. We had the normalization condition on the squared term, so we got 1, 1, 1, 1. And of course, we know that 1 times 1 is 1, plus 0 or minus 0, doesn't matter. Plus another 1 leads us to a 2 inside the bracket. So we end up with a 2 magnitude A squared. Again, to be normalized, we had to set all of that equal to 1. Divide by 2, that gives us 1/2 magnitude A squared, which leads us to A equal 1 over root 2. I think this is pretty well expected if you saw what happened in the spin states and the duplets there with the singlets, duplets, and triplets, things like that. Always good, always fun. That being said, this is misleading if A is complex because you still need a phase factor, which we've seen earlier, either in Chapter 3 or Chapter 4. Can't remember right now. But just be aware, if A is complex, there will be a phase factor. But for now, we'll just assume it's real because you're not going to lose generality with it, and you'll be good to go. Now, part B, as they stated, if we have psi A equals psi B, this is the same state, and this infers bosons because fermions cannot take the same state. They are antisymmetric, Pauli exclusion, all that fun jazz. So what we need to worry about only is the upper signs. So if we look at the wave function from 5.17, we see that we just want the plus sign. So we have a plus sign here, and we're good to go. Now set psi A for psi B and everything, and we see we have A at position 1, A at position 2, A at 1, A at 2, so we just have 2 of them. We're good to go, and now we can find a magnitude with really no worries. That being said, seem to have missed something here. We did find our first A, which brought us to stop 2. Goofy me. Oh well, we're having too much fun getting into the heart of it. Alright, so that being said, let's get on with the magnitude because this is the nasty algebra that tends to aggravate everybody. We see A star A, again A squared there. We have a 2 and a 2, so that gives us the 4. And then we're just left with A star at 1, A star, and then A at 1 again, so we have magnitude A squared, magnitude A at 2 squared, easy peasy. Run it through the integrals again, normalization condition comes in, and we see that we just get 4a squared times 1, leaves us with 4 over a squared. Divide it, divide over that 4 to the 1 over here. You get 1 over 4, take the square root, and you're left with a equal 1/2. Not bad at all. Not bad at all. And I'd say this is a great jump into the messiness that is to come with these particle systems. And as you might imagine, the potentials for these systems can get really messy because we have the potential of each charge, so that's 2. Then you have the mutual attraction term or repulsion term. So that gives us 3 terms in a potential. So just remember that these things get very dense to deal with very fast, and so all we can really hope to have is approximation schemes, which I hate to segue the other math papers, but these approximation schemes are going to make or break us in our efforts to gain better insights, because solving analytic solutions becomes over complicated and may not actually give us the same time value of approximation value that we can get running computer algorithms. So just be in mind, approximations and perturbation theory tend to be in all of our classes going up into the higher levels and more elaborate schemes. Got plenty to do with those, but that'll be the end of this video, so thank you for watching. Oops, more checkpoints. We found both of them. Cool. All right. So that being said, thank you for watching. Sorry for being rusty and tired on this return, but very excited to get back into this chapter. Lots in it, you know. And I really do have to thank all the patrons and all their supporters of this channel that has helped it grow to this point, because even while working and crazy, having y'all there to have conversations with and just keep discovering topics or new articles or new perspectives is always fun. So thank you again for all the supporters. As always, books, notes, and other reference materials are found below in the description. If you have any questions, please feel free to reach out. This stuff is fun. Learning is fun, and I wish we could just have fun learning instead of just trying to get through a test. It's a lot more genuine that way, I believe. And as always, thanks for watching. Until next time, stay curious.